Hello students, welcome back. We just went through a review and now let's go over to the new topics of Module 6, and that begins with the concept of dimension. Let's begin. Let capital V be a vector space, and we say the dimension of capital V is n, and we write like this: dimension of V is equal to n if the vector space capital V has a basis v1, v2, v3 all the way up to vn. If so, then we'll say the dimension of original vector space capital V is n. Now, what kind of example can you think of? Well, here's one. Rn has basis e1, e2, e3 all the way up to en, where e1, e2, e3, those are standard unit vectors. E1 is 1, 0, 0, 0, 0, that thing. E2 is 0, 1, 0, 0, 0, 0. And then E3 is 0, 0, 1, and then 0, 0, 0, all 0. And finally, En is 0, 0, 0, 0, all 0, except the last one, 1. How about the next example? The space of matrices, m by n matrices. Similarly, we have all these spaces matrices because there are m times n slots. Just 1, 1, and then everything else is 0. So we have m times n dimensional vector space. The dimension concept is not always valid here. Here's an example. C0 of interval 0, 1 to r, that is set of all continuous real functions defined in the closed interval 0, 1. And we consider C0 r, r before, defined in entire r before in module 5. This time, this is just a little wrinkle. Anyway, this thing does not have any finite set of bases, so it's an infinite dimensional space, or in our point of view, the dimension concept is undefined. Finally, here's an interesting problem. Set of all polynomials. Set of all polynomials, say for example, we have polynomial addition and scalar multiplication, and you can prove that those actually form vector space. It's not too difficult to do that. And any polynomial can be written like this: a0 times x to the 0 power plus a1 times x to the first power plus a2 times x to the second power, and then dot dot dot, and x to the nth power. Any polynomial of degree less than or equal to n can be written like this. Now, if the last coefficient an is 0, then the degree is less than n. It could be n minus 1 or even further smaller. For example, if everything after a2 is all 0, then we have just quadratic function, and that has dimension, that has degree 2, excuse me. Anyway, what's the dimension here? Basis x to the 0 power, or 1, x to the first power, or just x. Excuse me, a typo. Sorry about that. Alright, now everything looks good. Anyway, x to the 0 power, x to the first power, x to the second power, all the way to x to the nth power form a basis. So this is an example of a n plus 1 dimensional vector space. Set of all polynomials with degree at most n. By the way, the set of polynomials, that's going to be an important group to work on in abstract algebra. And it's a group, and also it's a ring, also it's a module. Oh well, I may be opening a floodgate here. It's going to be important in abstract algebra, so it's going to be good to remember this. Anyway, we just went through the concept of dimension and then went through the examples of n-dimensional vector spaces, but there is a problem, still a huge problem, because this description, which I'm no longer calling a definition, depends upon the choice of basis, v1, v2, v3, all the way to vn. Now, what if this kind of basis does not exist, like this case? Well, in that case, the dimension concept is not well defined, and then infinite dimensional space, we can move on. But we may have bigger problem. What if we have another basis, W1, W2, W3, all the way to Wm, for example, where m and n are different? How about a basis with 3 basis vectors, and then also a basis with, say, 7 basis vectors? What's the dimension of that vector space? Is it 3 or is it 7? Neither? Of course, not well defined in that case. So in order to have a well-defined concept of dimension, we have to have this uniqueness. If we have 2 different bases, we still have to have the same number of basis vectors. Or vector space V has a basis V1, V2, V3 all the way to Vm, and another basis W1, W2, W3 all the way to Wn, then m and n have to be the same. Therefore, we have unique number to define. So this description over here is now well defined. And finally, I call it definition. And I just copied and pasted the same statements there. So over here, there's a reason I use 1.0. It's not perfect. It's a good idea, yes, but it is not well defined by itself. You have to prove it first, and then you can define it. Okay, how do we prove it? Well, we need this lemma. Let capital V be a vector space, and V1, V2, V3, all the way up to Vm generate the vector space V, and let W1, W2, and Wn, all the way up to Wn, those are linearly independent. Then m is greater than or equal to n. Let's assume we have done that. Okay, let's assume we have done that. And then let's go ahead and prove this theorem 1.2, the uniqueness of dimension. By the way, what is a basis? Linear independence and generating put together. Remember that, please. And then here, what do we have? These generate, and then these are linearly independent. All right. We used both concept, generating and linearly independent, but not at the same time. Now let's come back to here. This is basis, so it generates and linearly independent at the same time. And this one, it's another basis, so generate and linearly independent at the same time. Now, how do we prove this? How do we prove m and n are the same? We're going to be using 1.1, but this time, among 2 concepts, we use generating. So V1, V2, V3 all the way to Vm generate V. And then for this one, we use only linear independence. W1, W2, W3 all the way to Wn are linearly independent. Exactly the same setting as 1.1. Consequently, m is greater than or equal to n. Now, let's use the same theorem 1.1 or dimension lemma in a little bit different point of view. For this basis, we used generating and we didn't use linear independence yet. For this one, we use linear independence but not generating. So we use the other things. So capital V is generated now by W1, W2 all the way to Wn. And then V1, V2, V3, and Vm, this is linearly independent family. Then, by the same idea, now n is greater than or equal to m. So what conclusion did we get? M is greater than or equal to n, and then also m is less than or equal to n, therefore, conclusion, m and n are the same. That completes the proof. And the implication of this proof, that allows us to define the concept of dimension like this. If it has a basis, V1, V2, V3 all the way up to Vn, then another basis, or still other bases, they all have the same number of basis vectors. So we're going to call that common number of basis vectors as the dimension, and we're going to write it as dimension of v is equal to n. That's how we define dimension. Let's recap. From a vector space, we defined or we described the dimension concept as number of basis vectors of a basis. But there's a bit of a problem. What if I select different basis vector? So we're going to prove a certain technical lemma that if one set is a generator and another set is linearly independent, then m is greater than or equal to n. We prove that, which we will do in the next video. And then use that to prove this uniqueness of dimension. We use generating here, linear independence there to conclude m is greater than or equal to n, and vice versa. Generating here and linear independence there to conclude n is now greater than or equal to m. Consequently, m and n are the same. So what's the implication from there? No matter what basis I select, same number of basis vectors. So that common number is now going to be called as a dimension. Now the concept of dimension is well defined. And all these examples now make perfect sense. Looks like everything is done except this dimension lemma, but this is going to be difficult, so we're going to do this in a separate video.